Now we shall look at question 7 from the exam. Question 7 is based on integration. In 7 part A, there are 3 integrals presented for you to carry out. The first one in part 1 is quite straightforward. You're asked to integrate the exponential of the logarithm of x divided by x. Probably the simplest way to tackle this, the second version here, of the solution is to notice, of course, that the exponential and the logarithm are inverse functions of one another, so that the exponential of the logarithm of x is simply x. So that simplifies the integral to the integral of the constant function 1, which has an integral of x plus an arbitrary constant of integration c. Alternatively, if you haven't spotted that, you might tackle it using integration by substitution, where you would introduce a new variable, which is the argument of the exponential, namely the logarithm of x. So if u is equal to the logarithm of x, then the relationship between the differentials is du is equal to 1 over x dx. And making that substitution, then the integral transforms into the integral of the exponential of u, du, the x's cancelling, and the integral of the exponential, well, it's a definite integral, is simply the same exponential of u plus arbitrary constant. And remaking the substitution, then the exponential of the logarithm of x would reduce to x. In part 2, we're presented with a definite integral, the integral from 0 to 1 of the square root of 1 minus x squared dx. This is handled by performing this trigonometric substitution, x equals sine of u. So let's look sorry, I need to reload this. Sorry, I've made some corrections there, so this is the correct version of the solution here. Here we go. So we're making this substitution here, x equals sine of u. Well, if x is equal to the sine of u, then the relationship between the differentials, take the differential of both sides, we have dx is equal to cosine of u du. Then transforming the integral, well, square root of 1 minus x squared is going to transform to 1 minus sine squared. Du becomes, so that should be dx there. Okay, sorry about that pause, just made a slight correction here. So the integral from 0 to 1 of 1 minus x squared dx, and 1 minus x squared is going to become 1 minus the sine squared of u, and the differential of dx becomes cosine of u du. Now, of course, we also have to transform carefully the limits of integration. So in the original integral, x increases from the beginning value of 0 to the ending value of 1. Well, if x is equal to sine of u, that can be achieved by increasing u from a starting value of 0 up to pi over 2 radians. Because when you take sine of that interval, sine of 0 is 0, and as u increases from 0, the sine value increases, and when u hits pi over 2, sine pi over 2 is, of course, 1. Okay, so that transforms our integral, and it initially looks more complicated still, but there are some simplifications that happen here. 1 minus sine squared is of course equal to cosine squared. So having cosine squared beneath the square root, then it becomes cosine of u multiplied by the cosine of u that's already here. We then have cosine squared du. The next step then is to use a trigonometric double angle formula, which says that the square of the cosine of any angle is equal to a half of cosine of twice the angle plus 1. So we perform that substitution here. So we replace cosine squared of u with cosine of 2u plus 1, all multiplied by a half, and bring that factor of a half out to the outside of the integral by linearity. And now this integral can be carried out using just some standard integration results. So the integral of cosine of 2u is sine of 2u over 2, and the integral of constant 1 is simply u. This gets evaluated at 0 pi over 2. Now, the sine part will be sine of 0 and sine of pi, both of which are equal to 0, so we don't get any contribution from this part here. And evaluating u at these limits simply gives us pi over 2, pi over 2 minus 0, so pi over 2. And this needs to be multiplied by a half, so we get our final answer of pi over 4. Then we go on to part 3. Part 3 is probably the most straightforward of all these, where you're integrating. So another definite integral, integrating from 0 to 1, 3x squared plus 2/3 of x plus the square root of x plus 2 dx. This can just be integrated immediately. We might consider the square root of x to be x to the power of a half, so all of these parts can be handled using just the standard rule for integrating powers of x. So you can see how it's treated over here. We're using linearity of integration, of course. The integral of the sum is just the sum of the various integrals. Integral of 3x squared is x cubed. Integral of 2/3 of x is 1/3 of x squared. Integral of x to the power half is 2/3 of x to the power 3 over 2. And the integral of 2 is 2x. And this is evaluated at the limits of 1 and 0. We evaluate it at 0 because there's a factor of x and everything. You just get 0 when you do the evaluation at 0. So we just have to substitute in x equals 1 to get the value of the integral. And we do that, we get 1 plus 1/3 plus 2/3 plus 2. Which, yeah, 1/3 plus 2/3 is of course 1, so 1 plus 1 plus 2 gives us our final answer of 4. In part B is a geometric application of integration. Here, where it says a semicircle of radius a, specified by this formula here, so y of x equals the square root of a squared minus x squared. So this is the semicircle lying above the x-axis, and it intersects the x-axis at x equals minus a and x equals plus a. So it's the upper semicircle of the circle of radius a centered at the origin. And we're asked to obtain an expression for the surface area of the sphere that's generated by revolving this semicircle all the way about the x-axis. And represented here with the general formula for the surface area of the surface obtained by revolving the graph of the function given by y of x around the x-axis between the limits of minus a and a. So we just simply have to substitute this expression in here into the formula and simplify as much as we can and carry out the integral and hopefully get a nice answer. So applying the formula here over here in the solution, let's just expand it a bit. So we have the surface area is 2 pi, the integral from minus a to a, y of x plus square root of 1 plus dy dx all squared. Okay, that's the formula. So putting in the definition of y of x, we have the square root of a squared minus x squared, 1 plus the derivative of the square root of a squared minus x squared is of course 1 over the square root of a squared minus x squared multiplied by minus 2x on the top. But then all of that gets squared, of course. So, and the 2's cancel by the factor of a half that comes down when you differentiate the square root of a squared minus x squared. So, simplifying that a little bit here, underneath this second square root, you've got the expression 1 plus x squared divided by a squared minus x squared. Well, that simplifies further, so we take this expression here, write it as a single fraction, so over the common denominator of a squared minus x squared. In the numerator, you can have a squared minus x squared plus x squared, so the x squareds cancel. In the numerator, you simply got a squared a squared. But now in this product here, you've got square root of a squared minus x squared in the numerator position here, and in the denominator position, you've got that same quantity again, the square root of a squared minus x squared. So those are going to cancel. Just going to be left with the square root of a squared, so in other words a. So actually the integrand simplifies all the way down to just simply a. So we're integrating constant function a with respect to x from minus a to a. So the integral of constant function is simply a times x, and then doing the evaluation here is just going to be multiplied by the length of that interval, which is of course 2a. So we have 2 pi multiplied by a multiplied by 2a. So this in total gives us 4 pi a squared as the expression for the surface area of the sphere of radius a, as expected.